All right, good morning, everybody. We are, first of all, needing to check the schedule. We're here on February 21, and, for the past couple of weeks, it's been kind of a try to catch up and cope with the one day that we were off. So, I suppose it would be possible if I really rip through things fast to finish up today. I don't want to do that. You'd be left reeling. So I think what we'll have to do to keep everything on schedule is, well, first of all, leave all the due dates the same, so it's all predictable, it's all within the framework that you're expecting. I will continue to finish up the new things on the 24th in the time that's scheduled for review. We will still have review, but I'll need to go back to an old technique that I used a number of years ago, and that is to have review sessions outside of class. And I'll do several of these so that as many people as possible have an opportunity to come, and I'll put up recordings of them on D2L so everybody will have access one way or the other. Please be thinking between now and Monday, which is what? Yeah, the 24th. Be thinking between now and Monday the 24th when a review session might work for you, especially in the evenings. I'd be willing to do one Monday evening and Tuesday evening. That'd be the 24th and the 25th. That'd be 2 evening sessions. If there was a sizable demand, we could, cram one into a late afternoon time or early morning on Tuesday or something like that. I'll have to kind of wing this come Monday when I poll you and see who would fit best into which time slots. But that'll keep us on schedule. Quiz 6 will still be due on Monday, and the way that'll need to work in practice is I'll just do it with you in class, and if you're here, you get full credit. There's no time to take it in, grade it, return it to you by the exam. You need to have it with you as part of your study material. So we'll just turn it around in class if you're present. If you can't make it, if you plan on not making it, it'll still be due. So everybody will still need to be present if you don't turn it in online. Okay, that's a way of coping with the schedule so that by the time we get here, our behindness from that one day off is erased and the rest of the semester is just on track without drama or changes or announcements or anything like that. Okay, any questions about that? All right, be thinking on Monday so that you know how to review. And here's just a quick little review from what we were talking about before. This is problem set 10. You will need to hand these in by the end of class today. And again, the most difficult part of these problem sets seems to be for everybody to get their name there. Please give me that. And, you know these? Yeah. All right, so let's draw the mirror image of this compound and then assign the absolute configuration. So the mirror image means just draw a tetrahedron. And this one has the solid line, the one's in the plane with you. It has it next to the mirror, and then as far away as possible from the mirror is the dash. So the tetrahedron is sitting with one thing coming out at you, one thing going away, 2 things in the same plane. All right, then you stick on the things that belong where they go. OH is clearly up top. CO2H, I'm just going to abbreviate this as that. You could put it COOH if you want to. That's a little bit sloppy, but not too bad. Far away as possible is methyl, then coming out at you is hydrogen. All right, if you can draw that, you're good. Let me draw this a little more neatly, okay? I'm promoting bad habits by drawing this. That's prettier and more accurate. All right, then the next stage is to assign an absolute configuration. Pass that back. Absolute configuration means that you're going to put a number on it, and I won't go through this in any detail because we've done most of this before, almost exactly. First atom out, away from the chiral carbon, is oxygen, carbon, carbon, hydrogen. Hydrogen has to be the littlest. Oxygen has to be the biggest. Then the other two are tied. 2 carbons, but going farther out immediately gets you to the conclusion that this one is bigger. So that'd be number 2, this would be number 3. Here's number 2, here's number 3. All right, and those numbers, of course, are moving toward the answer to question 2, which says, assign the absolute configuration. And so here's what you're trained to do, and it's not wrong. You do it like this. Let's see, I drew these 2 backwards. Sorry, that should be 3, that should be 2. So you're going to do this, and there are your circles. And here's your temptation, and the whole reason for setting this one up as an example. Your urge is going to be to go up 1, 2, 3 in that direction. That must be R. And this one, turning steering wheel to the other direction, would be S, but it's not that way because the little guy, hydrogen, is out at you. So here's what to remember. Priority number 4 isn't back. So make sure that you reverse the direction of these 2 little squiggles, looking like that. This one right here is not R. Instead, it's S. This one is not S. It's R. Everything worked, everything does work exactly the way it should. Draw things where you need them, put numbers where you need them, draw circles. But if your lowest priority group isn't back, you're looking at it from the wrong side. But that's okay. Just remember to reverse, and you've got the right thing. Either that, or if you're this awesome, envision turning it around in your head, or something like that. Redraw it. But it's usually just easier to think, where's my little group? Is it forward or is it backward? You know, where it ought to be. Okay, are there any questions about that? Yes?
So if it's going clockwise and it's R, and how do you
Yeah.
know what's reversing?
If the little group is out at you, see the hydrogen number 4 that's on the wedge coming out at you, it shouldn't be there. It should be going away from you. But sometimes nature doesn't hand us things drawn the way we want them to be drawn, or sitting the way we want them. You have to be prepared to look at it from either side. That's the idea.
So we remember if it's one of the shaded countries and reverse it, and it's not the same.
The shaded wedge is, yes, this one is out at you. You reverse that if number 4 is on it, because number 4 really should be here. When you look at 1, 2, and 3, the assumption is number 4 is back away from you. But the drawing doesn't always have to be that way. You can cope with it either way, as long as you remember. Okay, any questions? All right, so how about if everybody passes those this direction in your row and pick them up. All right, we'll pick up here where we left off. Before get most of the way done today, and for sure finish up on Monday. Is that everybody from over here? Yeah. Okay, good. All right. We've done all the talking we need to do about drawing pictures of stereoisomers, relating them to each other, and so forth. So how are they different? Well, now remember that we have 2 kinds of stereoisomers, and I'm going to start off by comparing those 2 to each other. And the kind we just got done doing is the review, so that's fresh in mind. I'll start with this one. These are the guys that are mirror images of each other. Diastereomers are not mirror images of each other. Haven't really drawn many of these yet, the diastereomers, but we will. And the good news is the diastereomers, they're not hard to tell apart physically at all. They'll have, different melting points, different boiling points. You can tell if it's pure or not by measuring a melting point, and they'll react chemically at different rates, totally different compounds from each other. Those are the easy ones to tell apart. The hard ones are the enantiomers, which are the ones that we just drew and we've put so much time into dissecting. It's like 4 things on the same carbon, and the only difference between them is where they point in 3-dimensional space. These things are hard to tell apart. They'll do the same thing in reactions. Their rate will be the same unless they're reacting with another chiral compound. And that's about the only way to tell them apart chemically. Physically, the only way to tell them apart is with a special kind of light. But let's talk about how they're not different. If you draw 2 enantiomers like these 2 that we just did, those 2 right there would have exactly the same melting point and boiling point. You could have a 50-50 mixture of the 2. You'd have no idea how pure it was from the melting point. So melting point, that's not going to help you. What will help you is the way they interact with not just any light in the world, but a special kind. It's called plane polarized because it's organized. It's not just like the light in the room. Light in the room is, going every different direction. You start out with ordinary light, either from the room or a lamp, and you've got waves that are, oscillating in all possible directions like this. Well, that's okay. It bounces off everything in the room. We can see it. If you run it through a polarizing filter, you will then have light that is nice and lined up with everything in phase. It's a much not much will come through the filter, but it'll look like this. And that's what the filter does, and it produces light that's so-called plane polarized. It's this right here, this kind of light, to tell. Now this is the special kind of stereoisomers. Tell apart the enantiomers. That's what it takes to tell those guys apart. Okay, now you can't go to Walmart and get plane polarized lights. Okay, it's going to take some specialized equipment to do it. On the other hand, it's not that expensive for an instrument. We have one here in the department. I forget if it's working at the moment, but this is doable. So here's the way you use it in practice. You're going to start out with this special kind of light, which is made for you by an instrument, and we'll just kind of take that for granted. So this is made by a filter. And if you run it through one enantiomer, you're going to rotate light clockwise, and I'll see if I can color the main difference between these two, or counterclockwise, depending on which enantiomer you're dealing with. Now, keep in mind, the whole difference that we're doing, because we're caring about this, is, say it's something like this, trying to tell apart these 2 enantiomers. That's the whole reason to do it. So it could be either R or it could be S, not both. If you're given this, then you automatically know something about the other enantiomer, and I'm going to map each one of those 2 configurations, R or S, to what you know about the other enantiomer. This one is this one would be S, and this one would be R. About the only thing you can tell about these 2 in advance is these 2 are guaranteed to be opposite. And literally, it's light that's lined up in a plane like this. It goes through the filter, through a solution of the enantiomer, and okay, imagine my hand is the plane of the light. It comes out like this, or it comes out like this. It can be pretty subtle, but it sure is handy if you need a way to tell these 2 apart. To begin with, here's one thing that you want to avoid. I'm not going to write it so that it doesn't introduce the confusion. You don't want to get into the habit of thinking that if you see a clockwise rotation, which we symbolize with plus, or a counterclockwise rotation, which we symbolize as minus, you don't know if that is R or S to begin with. It sure would be nice if we could say that all the clockwise plus rotations in the world were R. Or maybe we could say all the clockwise rotations are S. But wouldn't you know, nature is not that easy to pin down. Sometimes you can see a positive rotation and you do the measurement and you discover you're dealing with the R enantiomer. Sometimes it's the S. But the good news is once you know, one way or the other, the opposite configuration must be the opposite rotation. That's about all you know. You have to be given, to begin with, a sign and either R or S. Otherwise, you can't tell. Now, I would say that very confidently at the beginning of my career. There was a computational method published a few years back that kind of allows you to predict R or S and connect it to plus or minus. But for purposes of this class, you don't know. You've got to do a measurement. Okay, and there's a way to put a number on this. It's like a rating for each enantiomer, and it's this little formula. Please don't memorize it. If you need it, it will be given to you on an exam or written on the board or something like that. We're going to concentrate not on memorizing it, but on using it. So we're going to, like this says, we're going to quantify how much light rotates. And there's a symbol that goes into this. So this whole thing right here, alpha D in 25, has a little term that goes into it. It's called standard rotation. And it's going to be, start out with a number of degrees. So in degrees, and it will need to be either plus or minus. So either to the right, clockwise for plus, or the other direction. Then there are a couple of other things that get plugged in, both of them on the bottom. So this first one here, the length of the sample, no big surprise, the more sample you've got in the instrument, the more the whole plane rotates. This will need to be in, I didn't make this up, so don't blame me, in decimeters, tenths of a meter. I don't understand who came up with that as the standard, except maybe it was easy. They only had a 1 decimeter cell, but that's the standard. The concentration of the cell, of your sample in the cell, is usually going to be in grams per milliliter. All right, so this whole thing is bound to be plus for one enantiomer and negative for the other one. That's all you need to know. That's all you can know. And here's another way to reiterate. If you start with R or S, you cannot predict plus or minus. It can be one or the other. Just accept that fact, embrace it, live with it, and learn to use it. Okay, and here's the big difference between these two statements. One of these two enantiomers, either R or S, will have one sign. The opposite configuration, S or R, will have the opposite sign. Sorry, that's all nature allows us to predict. I want to run a few numbers through that formula, give you a chance to look and see what it says. Okay, here's how to dissect a problem that's thrown at you like this. So you make a solution by dissolving 15 grams of this stuff, and maybe the first thing to notice is this little symbol right here, S. What that's telling you is that you are now dealing with, let me say, just one enantiomer. There would be another one, which would be called R, but somehow you've gotten a hold of this stuff and it's just the S enantiomer. And you dissolved a certain number of grams in 100 mils of water in a 1 decimeter cell. All right, now this will be an example of how you can use the formula, maybe even rearrange it if you need to, but plug the numbers and you'll be given this to start with. So starting out is alpha D25, that's standard, and it equals the observed rotation, and you're going to divide through by length times concentration. Okay, now what we're asked to solve for is this thing right here. Okay, we're asked to, I'm sorry, it said calculate this. We're asked to calculate this. All right, that means, and let me highlight this in a color, rearrange to this. You want it to say observed rotation equals something all by itself. And so the easiest way is to move the bottom here so that it multiplies the original left-hand side. Okay, so do something like this. Alpha D25 times length times concentration will equal the observed rotation. All right, now if we're asked to solve for that, then the rest of those numbers had better be in there and just drop out so that they fit into the rearranged version. Okay, alpha D25 is given to us here. This is your minus 2.6 degrees per deciliter times gram per mil. Gotta love those units. Okay, they'll cancel out if things go well. And then the length of the cell is this spot right here, so 1 decimeter. And then the last spot, the concentration is going to be 1.5 grams per 100 mils. Equals. Okay, that'll be the observed rotation, which by my calculation was minus, some of you might want to check me on this, and the important thing is the minus, 0.39, and then the units are going to be just degrees. So that's worth a comment all in itself. Okay, here's your result. And there are two things probably to point out about it. The first one is the sign. The sign is negative, and it had better be because we were given a standard value of minus 2.6. So the whole sample, even if it's not standard concentrations, it better at least be in the right direction, and it is. The unit right here, the unit is just degrees. And that kind of makes sense, because what we're looking at is just a rotation. So rotation of light by some number of degrees. As with any calculation, if you get the right sign and you get the right units, that's some indication you're on the right track. So start with that anyway. Okay, using that definition, we can get to something called, this is the last use we'll make of this number, something called optical purity. And it means the relative amounts of two enantiomers, which are bound to be R and S. If you want to know, you're looking at a sample, how pure it is, sometimes that's really important. In fact, sometimes it turns out in the past it could have been either fatal or therapeutic. All right, so here's how you start. 100% 1 enantiomer earns the term enantiomerically pure. Okay, 1 enantiomer only, and that means none of the other enantiomer. That's the dream. Okay, or maybe it's not, but in many cases you need one thing that's pure. A racemic mixture is what you have. It's the term you apply to 50% R and 50% S. So if it's a perfect mixture, it's a total mess. Maybe you don't care. Maybe it doesn't need to be one or the other. But that's the two extremes right there. That's about as, those are the two extremes. So here is how we define optically pure. We come up with a number that we call enantiomeric excess. And again, this is a formula that you don't memorize. It'll be written for you on the exam itself, written on the board, something like that. You'll have access to it. What you're going to do is start off with two numbers that you will need to know. Here is the number of moles of 1 enantiomer, and you start with the one that's your major component. So 100 is the dream. The minor component is the other one. You take the difference between those two, and then you're going to divide through by the total number of moles of both enantiomers. Now, your best case scenario is 100%. And the worst is, and that means all 1 enantiomer. Okay, so if you don't know the number of moles, you can at least estimate the difference between those two, because this version of the formula right here says, oh, you don't even have to know number of moles. This version just requires that you use your measurement, your instrument, to measure rotation. So here's version 1, here's version 2, and the good news is that, even if you don't know the number of moles, as long as you can measure observed rotation and you know what it should be, because you know a standard value, this is what it should be, and this is what it is, you can do that comparison. Okay, that's a way to measure the optical purity of this precious sample, which may have been really expensive to make. And if you're making it and you care about enantiomeric purity, you are probably intending it for some kind of biological evaluation. An amino acid would be a main suspect. So I think there's room for one little example of that. No, I guess I didn't do an example of that one. But there will be one to do on a practice problem, which we'll do on Monday, as well as on the quiz, which we'll also do on Monday. So start putting that in motion, practicing it, and getting a little experience and comfort with that. Again, these are formulas to use, interpret, and so forth, but not to memorize. Okay, so let's move on to something much closer to biology. And that is this way of dealing with enantiomers by drawing a funny version of them. And you may wonder, well, isn't it kind of complicated enough the way we've got it? Yeah, it is, except that everything we've done so far looks like this set of structures here in number 1, right? Okay, now just to, even though it's not really necessary here, it probably makes sense to start with just one chiral carbon in a molecule and then build up once you see how this works. What we're going to say is that we'll start drawing a tetrahedron as, this isn't very scientific, but the way I say it is a bow tie to begin with. All right, here's a tetrahedron, the way we've been drawing it. So we've been drawing it like that. And here is a way of redrawing the same thing. This is what is meant by the bow tie view of it. These two wedges are both coming out at you, and the other two positions are both going away. That's a totally valid way to hold a tetrahedron. It may not be quite as easy as this, but it's still true, and sometimes nature will face you with this thing. Well, once you've done that, people realized, as long as everybody knows what we mean, we can save ourselves the hassle of drawing the hatches and drawing the wedges if we just do this little cross. What that means is that you have two different categories here. These two are both really out, and these two here are both really back. It really is a tetrahedron, and it's going to do the same sorts of things. It can be analyzed and redrawn the same sorts of ways as what we've done before, but this is a shorthand, and you're about to see why there's such a big incentive to do it that way. The incentive is here in number 2. Everything we've done so far has been carefully limited to molecules with just one chiral carbon. But the real interest in nature starts in when you've got more than one in the molecule, and that's most of nature. So, all right, let's just do a little quick map here. This is our first victim of a compound that has more than one chiral carbon. It's got 1, 2, 3, and then 4, I guess. So that's a total of 4 carbons, not a very big molecule. And which one of these are chiral carbons? Well, not number 1. It doesn't even have 4 things on it at all. That's sure not 4 different things. Not in the running. 2, yeah. And 3, yeah. Because each one of them has a hydrogen, an OH, and 2 wildly different things. Number 4, nope. That one's a nope because that carbon has 3 hydrogens on it. They're all the same. Okay, so that's one way of drawing this thing. And what I want you to do is envision taking this version right here and redraw it as this, and maybe just let's keep the carbons, at least the first one. I'm going to keep it looking like it is, and I'll put a number on it. So there's the carbon with a double bond and a hydrogen, and there's its number. So there's 1, 2, 3, and then last, just to really identify where it came from, the drawing, that would be number 4. Skip those numbers if you don't like them. And so here are the chiral carbons, number 2 and number 3. Okay, now each one of those carbons, number 2 and number 3, you look at it in the drawing you're given to begin with, and what you can see is it has on it, each one of them has an OH and a hydrogen. Hydrogens aren't drawn in that first version. So one way to draw this would be like this. Say, okay, each one of those starred carbons is at a cross. So each star carbon is now at a cross in the drawing. And then you could easily, quickly, draw the enantiomer. Draw a vertical line, like right there. And we're going to put the same carbons all in a row. And there's 1 and there's 4. Now, you don't need to get too concerned about doing the exact mirror image within the group itself, such that it's okay to put C double bond O instead of the H. I've had students ask me, okay, do I have to put the H right there and the double bond O? No, not really. You're drawing the group as a whole. And then you draw these cross pieces lined up, as close as you can, so that it's clear what you're drawing the mirror image of. There's 2, there's 3. And this time, as always, anything that starts close to the mirror stays close to the mirror. Anything that's far away stays far away. Okay, again, right here, there's your mirror. Okay, now as before, we have two structures that are mirror images of each other. Compare these two right here. They are mirror images. If you tried to line them up perfectly, it wouldn't happen, because if you lined up the top two and moved this one over on top, you'd be trying to line up OHs over here and hydrogens here. It's like your hand. These two are chiral, so these two compared to each other are enantiomers. Okay, and that method of drawing things is the jumping off point into the next piece, which is drawing as a group molecules that have more than one chiral carbon. Now here the goal was just figure out a way to draw it and deliver the drawing. So as long as you're okay with what maps to what, you can leave the details for a little bit later. This, by the way, is something pretty close to a carbohydrate. A carbohydrate is bound to have, if it were a real carbohydrate, it'd have an OH there. But other than that, this is what carbohydrates start to look like. They're aldehydes or ketones. That aldehyde is that little group right there with lots of OHs. Okay, let's put this in motion. And I'm going to ask you to generalize and think about more details than ever here. Okay, thinking about molecules with more than one chiral carbon means that we're going to be talking about terms that kind of hit before, and we'll work those out not so much as definitions but as descriptions. Once we get to them and you can see what it looks like, we'll put those terms in place. Okay, we're headed for bigger molecules, and here's a little rule that you want to remember. I saved plenty of room for this little formula right here. Okay, the maximum number of stereoisomers you can have for a given molecule is 2 to the n, and the number of stereocenters is the same as the number of chiral carbons. Stereocenter is the same term as we'll be using it in this class. Here's the max. Now look out, because the actual number may be smaller than the max. So there's what you want to take as your starting point. And by the way, memorize that one. Yeah, that one's couldn't get much easier than that to memorize, right? So we'll use that as a destination and start talking about what it looks like. You'll have to do a little comparison here. Sometimes you'll draw some structures and you'll discover I do have the maximum number of stereoisomers. They really do exist. Sometimes it'll be, uh-oh, there's one missing. We'll get to that case too. Okay, so here's how it works. Here's the first example. I simplified this one compared to the Fisher projection that we just drew, to start with anyway. And here's an example of a compound that has 2 stereocenters, 2 chiral carbons in it. And it's going to look like that. Now, that's not all the carbons. I didn't star all the carbons because only 2 of them are chiral. And so here's all the stereoisomers that you can envision. Let's start out, well, I'm just going to do it the easy way. I'm going to say that to begin with, the OH and the chlorine could both point forward. The next possibility, you don't have to do it in this order, but would just be leave one of them same, switch the other one. So I chose the OH, it's staying put, and the chlorine, that's the one that flops back. The next one Maybe change the story on your OH and say sometimes it can be back, so could the chlorine at the same time. And then the only other possibility would be the OH back and the chlorine forward. Okay, now look at this. 2 to the n in this case is 2 squared, which equals 4, and this 2 right here, remember, is going to be your number of chirocarbons. There are 2 in this compound, 2 possible, and lo and behold, you can draw them all out. They all are really looking different from each other. So here's approach number 1. Make a list. And that's okay. That's not wrong. Here's a simpler, quicker way to do it, and that is to do this. I'm going to say on either end here, we've got a methyl group. And one way to start out is to just not trouble yourself about which one of these 4 you have. Just start with something that's easy. And the easiest thing that I can think of is to go, well, we'll take both of these special groups, the OH and the chlorine, put them on the same side, close to the mirror. Each one of those same 2 carbons also has a hydrogen, of course. Your mirror image would just look like this. So there's one pair. What we're now headed into is the other option for drawing. Instead of just trying to wade through all 4 of them, just draw a couple of pairs. So another way we could have started would have been like this. These are the terminal carbons, number 1 and 4, in place. And the other way I could have started was to say, well, they're not on the same side, the OH and the chlorine. Maybe they happen to point in different directions, so they would look like this to begin with. Your mirror image would also be reversed. And at that point, yeah, remember your hydrogens, but you'll have 2 different pairs, and there's a relationship between these 2. It sure was easy to come up with these 2 pairs just by, reflecting across a plane. You don't have to draw wedges and dashes or anything like that. But you've drawn 2 things that are not superimposable. If you tried picking up one of these and setting it on top of the other one, it wouldn't work. It's like your hands. They are chiral, so these 2 compared to each other are enantiomers. They are stereoisomers, and they are mirror images. It's like your hands. And the same goes over here, right? I drew them as mirror images on purpose. So these also, this pair, are enantiomers. But you also need to be able to say something about, what about we cross pairs here? We cross the boundary. They're all stereoisomers of the same thing, right? It's just 4 carbons in a row with an OH and a chlorine on the middle too. What you can say is, if you compared, say, the first one here to the first one here, are they stereoisomers of each other? Sure. Different things on the same carbons pointing different directions. Are they mirror images? They aren't. So these 2 are definitely not mirror images. So this pair are, and here's the term, diastereomers. All right, now you could really clutter this whole diagram up if you wanted to. Anytime you cross between pairs, you're talking about diastereomers. This one and this one. This one and this one. This one and this one. All those stereoisomers, yeah. Mirror images, no. So that makes them diastereomers. The max that you can envision for this molecule is 4, and the actual number that we found just by drawing them is 4. We found them. And so you're going, well, how could you ever end up with fewer than 4? Couldn't you just draw them and come up with the right number? Okay, hang on. Let's do this same little exercise, but for this molecule on the next page. Heads up as you look at it to begin with. The two ends of the molecule are the same, and the two things in the middle are the same. I'm going to skip everything except this version of the drawing. So let's come up with a couple of crosses and do their mirror images. I won't ask you to draw many of these on a quiz or exam. It just takes too much time, but it doesn't hurt to kind of learn how to do it. Okay, so here's our suspects. There are the chiral carbons. Each one of them has a methyl, a hydrogen, an OH, and a whole bunch of other stuff on it. All right, so like before, we start off with a methyl group, and it's on either end. Maybe I should just bring back. See, the same here. The ends are the same. Go ahead and put that in on all these spots. And here's the little comparison we're going to do. We will know for sure what's the same across all of them. They both start and end with a methyl group. And then in the middle, you've got carbons 2 and 3. And both of them have an OH. So certainly do a mirror plane where you start out with both of them on the same side. Come back for the hydrogens in the middle in a minute. And really the only other way you could do this would be to say, well, I could have the two OHs on different sides from each other, and their mirror images would look like this. Here's a hydrogen, and here's a hydrogen. Okay, so you look at these two compared to each other, and you've carefully drawn your chiral carbons, your mirror images, and it looks to you like you've drawn enantiomers. Put the hydrogens in now that the framework is easy to see. And you've done everything right, and you say, are they enantiomers or are they diastereomers? And what would the answer be? I'm sorry, but the answer is neither one. These two are identical. You carefully drew all this stuff, and in doing that, you came up with a molecule that has, going through the other direction, a mirror plane. And that means that even though each half really is a chiral carbon, the two halves are mirror images of each other. And now here's a mirror plane dividing the two, and wouldn't you know, you could take this molecule right here, turn it upside down, and set it perfectly on that one. Oh man. Okay, these are identical. There's a term for this. They're called mesostructures. They are not enantiomers. They are not diastereomers. Those are things you can say that are true and then are not true about them. And having got to that point, which is as confusing as it gets, let's leave in a state of confusion, okay? I will see you on Monday and we'll wrap this up.